For most of human history, we viewed our solar system as a closed, clockwork mechanism, a fortress of stability governed by the predictable laws of Kepler and Newton. But as our telescopes have grown more powerful, peering into the infrared spectrum and utilizing the precision of gravitational microlensing, we have discovered that the void between stars is far from empty.
It is populated by billions of rogue planets, worlds ejected from their parent systems during the violent early stages of planetary formation. These are the orphans of the cosmos, drifting in the absolute zero of interstellar space. Statistical models now suggest there may be more rogue planets in the Milky Way than there are stars.
The most terrifying aspect of these objects is their invisibility. Unlike stars, they emit no light. Unlike traditional planets, they reflect no sun. They are detected only when they happen to pass in front of a distant star, momentarily warping its light through gravity. But what happens when one of these invisible giants finds its way into our neighborhood? This is not just a story of a space invader. It is an exploration of the fragile physics that allow life to exist. In a real-world scenario, we wouldn't see a rogue planet coming until it was already upon us. If it entered from outside the plane of our ecliptic, our current surveys might miss it until its gravity began to perturb the outer solar system. The first sign wouldn't be a new dot in the sky, but a statistical anomaly in the Oort cloud. A rogue planet of 13 Jupiter masses acts as a gravitational scythe, knocking thousands of dormant comets out of their stable orbits. The result, a storm of comets heading our way with little warning.
Some would be flung into the interstellar void, but others would be sent screaming toward the inner solar system. Long before the rogue planet reached Mars or Earth, we would see a massive spike in long-period comets. This would be the early warning system, a lethal rain of ice and rock that could last for centuries, triggered by a ghost we cannot yet see.
As the rogue planet enters the planetary zone, the space occupied by the 8 major planets, the clockwork stability of our system begins to dissolve. This is the N-body problem in action. In a 2-body system, like Earth and the Sun, orbits are predictable, but add a third, massive body, and the math becomes chaotic, meaning small changes in position lead to vastly different, unpredictable outcomes. Let's look at the object SIMP J01365663 plus 0933473. With a mass nearly 13 times that of Jupiter, it possesses enough gravitational heft to influence the Sun itself, causing it to wobble slightly around a new center of mass. As this object passes within a few 100 million kilometers of Earth, it doesn't need to touch us to kill us. Gravity follows the inverse square law. If you halve the distance to an object, its gravitational pull becomes 4 times stronger. Earth's current orbit is nearly circular, with an eccentricity of 0.016. The rogue planet's flyby would stretch this circle into an ellipse. This shift in orbital eccentricity is the primary engine of our destruction. We would no longer be on a steady path. We would be on a celestial roller coaster, swinging wildly toward and away from the Sun.
Once our orbit is stretched into an ellipse, Earth enters a cycle of extreme thermodynamic stress. At perihelion, the closest point to the Sun, the Earth would move at its maximum velocity. Even if the rogue planet only pushes us 10% closer to the Sun than we are now, the Stefan Boltzmann law tells us that the energy flux would increase significantly. We would see the rapid evaporation of surface water, the collapse of the polar vortex, and temperatures in the tropics reaching levels where human protein begins to denature.
What if Earth's orbit became a deep ellipse? The farthest point, called aphelion, would become a frozen nightmare. Kepler's second law dictates that the Earth must move much slower at aphelion. We would spend a disproportionate amount of our year in the deep freeze. As we drift out past the orbit of Mars, the amount of energy hitting our atmosphere would plummet. Solar constant would drop to just 30 or 40% of its current value. A new ice age would grip the planet. The oceans, which act as a thermal regulator, would begin to freeze from the top down. The ice albedo feedback loop would trigger. White ice reflects sunlight. The more ice we have, the less heat we absorb and the colder we get. This is a runaway process. Within a decade of the encounter, Earth could become a snowball planet, a gleaming white marble lost in a long dark winter.
The damage isn't just atmospheric, it's geophysical. The gravitational tug-of-war between the Sun and the passing rogue planet would exert massive tidal forces on the Earth's crust and mantle. We aren't just talking about ocean tides, we are talking about land tides. The Earth's crust could rise and fall by several meters every day. This would trigger unprecedented volcanic activity and global earthquakes. The ring of fire would light up. While volcanic ash might actually help block out the sun during the scorching phase, the resulting volcanic winter would only accelerate the freezing during the aphelion phase. C4 plants, which make up most of our food crops, would fail first. The collapse of the food chain would move from the land into the oceans as phytoplankton, the base of the marine food web, die off. From a biological standpoint, this is a great extinction event. How does a technological civilization respond to the loss of its sun? If a rogue planet pushes us out of the habitable zone, the surface becomes a graveyard of frozen nitrogen and oxygen. But kilometers beneath the surface, the Earth's core still glows at 6,000 degrees Celsius. We have only one choice. We must become an endogenous species, living off the internal heat of our planet. Survival would require a total mobilization of human resources. We would build geothermal vaults, massive underground cities powered by nuclear fusion and the Earth's own internal heat. We would replace the sun with LED arrays tuned to the specific frequencies needed for hydroponic farming. We would harvest the frozen atmosphere to create liquid oxygen. This would be a bottleneck event for humanity. Our population would likely shrink from billions to a few million specialists living in high-tech cocoons. We would evolve into a new kind of civilization, one that no longer looks at the sky for light, but looks to the mastery of the atom and the heat of the rocks beneath our feet.
The encounter with a rogue planet like SIMP J01365663 is a reminder that our Goldilocks existence is a privilege, not a right. We live in a brief window of cosmic stability. The universe is not a static museum. It is a dynamic, often violent laboratory of gravity and energy. While the odds of a massive rogue planet flyby in the next millennium are low, the threat is a mathematical certainty on a long enough timeline. It underscores the importance of becoming a multi-planetary species. If humanity is spread across the solar system, the disruption of one planet's orbit is no longer the end of the human story.
We are the only eyes the universe has to see itself. Whether we are basking in the light of a stable sun or huddling around a fusion reactor in a frozen world, our mission remains the same: to understand the laws of the cosmos so that we may survive them. Until the next what if. Keep looking at the stars, not just for their beauty, to watch for the shadows that move between them.